Welcome to the Latin America Regional Advisory Committee's Technical Webinar Series, Recent Advances and the Road Ahead. The SEG Latin America Regional Advisory Committee and myself, Lori Whitesell, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation followed by an extended question and answer session. Additionally, we will also take questions as we go. During the formal question and answer session, if you'd like to ask questions, please raise your hand in the webinar interface, and I will adjust your settings to allow you to ask your questions directly to the presenter. Today's presenter is Dr. JJ Sun, who is Assistant Professor of Geophysics in the Department of Earth and Atmospheric Sciences at the University of Houston. He obtained his Bachelor's of Science in Geophysics from China University of Geosciences in Wuhan in 2008, and his PhD in Geophysics from Colorado School of Mines in 2015. His research interests revolve around the theme of integrating various types of prior information into geophysical inversions for better characterization of subsurface geologic structures by utilizing tools developed in convex optimization, computer vision, pattern recognition, and machine learning. He teaches machine learning, electromagnetics, and potential field methods at the University of Houston. His current research focuses on tackling magnetic remnants problem by integrating geophysics and machine learning and developing joint inversion algorithms for integrated imaging of the Earth based on multiple geophysical data sets. He is an active member of SEG, a member of AGU and EAGE, and also serves on the SEG Gravity Magnetics Committee. He received honorable mention for Best Paper in Geophysics in 2015 and Best Paper in the Mining Sessions at the 2016 SEG Annual Meeting. So without further ado, I'll hand it over to our presenter, Dr. JJ Sun.
Okay, thank you, Laurie. Thanks for the introduction. Hello, everyone. So I'm JJ Sun. So today I'm going to talk about the work I have done in the past few years. So basically what we do is that we combine the geophysical inversions with the machine learning techniques, and we have developed a new set of inversion algorithms. So here is the outline of my talk. I will begin with a very brief introduction to the Tikhonov regularized inversion. That is probably the most classical and the most widely used inversion schemes. I'll also talk about motivation for developing new algorithms by presenting you a few motivation examples. So in my talk, I'll be focusing on unsupervised machine learning, specifically clustering. Then I will talk about the three algorithms that we have developed for solving different inverse problems. And if time permits, I will also talk about uncertainty analysis and conclude my presentation with some discussions and thoughts on the road ahead. So on this slide, you see this equation here, D equals F as a function M. So it turns out that many of the physical measurements based on a physical system can be summarized by this equation. For example, so here's this F, the symbol F that represents the physics that is involved in this physical system, and also the measurement. M, that is the parameters that we decide to use to describe any physical system. For example, in our case, geoscientists are interested in Earth. So this M could be a representation of the Earth, for example, using densities or conductivities. F could be various physical laws, and D could be the various types of geophysical data. For example, if we talk about gravity data, then D here represents gravity data. F is a mathematical representation of Newton's law of gravity, as well as the survey geometry we decide to use to do the forward modeling. And M would be the density distribution that we use to describe the 3D Earth. So this almost any measurement in physical sciences can be summarized by this simple equation. So when I say forward modeling, what I mean is that we assume that we know the physics well enough, and also we have assumed some distribution of the physical parameters that we think can be used to describe Earth. And the job is to simulate the physical responses or the geophysical data based on F and M. So that is forward modeling. And in geophysics, we are more interested in the inverse problem, in which we know we have collected some data, measured data D, and we also assume that we know the physics well enough, and we want to estimate the model parameters. So this is called inverse problem. This is many of the problems that we are dealing with in geophysics can be summarized by this equation here, where we know D and F, we want to estimate M. So speaking of the inverse problem, so here is the example. On the left-hand side, this is the airborne magnetic data collected over a IOCG deposit in Brazil. IOCG standing for iron oxide copper gold deposit. So this is the airborne magnetic data where we see this big anomaly here. In this case, we have the number of data we have is on the order of 2,000 thousands. So this is a 2D magnetic data that we collected over the surface of Earth, but we want to estimate, we are more interested in the 3D distribution of susceptibility of the Earth. So after applying inversion to this set of data, this is the final product. So this is a 3D volume that describes the 3D distribution of magnetic susceptibilities. So in this case, we are using susceptibility as the physical parameters to describe the Earth. But the challenges of the geophysical inverse problem, but we have a few challenges when it comes to inverse problem applied to geophysics. For example, the first one is the non-uniqueness. In the previous example, I showed you we have about 2,000 data, but we want to estimate physical parameters, 2.6 million physical parameters. So that is a underdetermined problem. And mathematically speaking, there are infinite number of models that could fit our data pretty well. So this is the terminology that we use to describe this is non-uniqueness. In addition to that, we also have the ill-postedness problem, meaning that small errors in data could cause a lot of changes in the model. That is something we want to avoid because we want our model to be stable or to be robust against the measurement errors. So one of the inversion scheme is called Tikhonov regularized inverse problem. So here I'm going to briefly talk about that. Remember, the goal of inverse problem is that we want to recover model from the geophysical data. And we want this model to be, first of all, to be able to reproduce the observed data to its noise level. Therefore, we have this data mixture term, which is simply a measure of the difference between the observed data and simulated data. But in the meantime, we also want our data to have, our model to have minimum amount of structure, because we don't want to overinterpret the data we collected, which always have noise. So therefore, we have this regularization term phi m, which is simply a measure of the amount of structure in the model. So what we do in practice is to combine these two terms, phi d and phi m, with another weighting parameter, which is also known as regularization parameter. So this is our final objective function that we want to minimize when solving geophysical inverse problem. This has been used a lot in geophysics. If you look at literature, there are a lot of successful applications of this type of inversion methods to many different types of geophysical inverse problem. So here are a few examples. On the upper left, this one shows you the seismic four waveform inversion result. So all these yellow anomalous bodies, these are the seismic shear wave velocity anomalies. So in this case, the authors, they use seismic data and they do the inversion and try to understand the mantle convection. And on the upper right-hand side, so this in this case, what you see here, this picture, that is the 2D distribution of the electrical conductivity by inversion of control source EM data. And so here the goal is to recover the sediments underneath the basalt. And this example here, in this case, authors inverted the airborne gravity gradiometry data, which is shown here, and they obtained a distribution of the density anomalies in the subsurface body, which helps them identify the potential iron targets. And this example on the lower right-hand side, so here the authors, they use the magnetic data, and they inverted the magnetic data, and they were able to recover all these anomalous bodies, which correspond to the kimberlites. So this has been this kind of Tikhonov regular inversion has been used a lot, but there's some problem with it. So here's a motivation example that I hope can help highlight some of the problems associated with the classical Tikhonov regularized inversion. So here on the upper left, I just simulated a very simple density model where we have a uniform or zero background, and we have two blocks. And also I simulated the gravity data and added some noise. So here on the lower left, this histogram, this shows the distribution of the density, true density values. So here you see two peaks or two spikes at 0 and 0.4. That's because in this true model, we want to have two possible density values, either 0 or 0.4 G per cc for the anomalous bodies. So therefore, you only see two spikes at these two locations. But if you if you implement Tikhonov regularized inversion, and this is what you get. This is what you would get. So here we recover. What you see here is a smooth version of the true model. This is very typical of any Tikhonov regular inversion because of the use of the smoothness-based regularization. If you look at this model, this is a good model because we recover the anomalous body with a reasonable shape and correct depth and locations. But if you plot up the distribution of the inverted densities, this is what you see here. So there are two problems with this model. The first one is that the inverted values are systematically lower. For example, if you look at the distribution of the anomalous density values, they are almost like uniformly distributed between 0 and 0.3 something. Let's say 0.32. None of them is getting closer to the true value 0.4. So that brings another problem. That is what I wrote down here. The statistics of the inverted densities are not quite consistent with the true distribution here. So the research question now is how to incorporate the following information into inversion. For example, what if we know that there are only two possible rock types in the subsurface? And what if we know that the mean densities are these two values, 0 and 0.4? So the inverted density value can only assume one of these two values. So how can we incorporate this type of statistical information into inversion? Well, this is important in several aspects because this will, if we were able to incorporate this kind of information into inversion, we will be able to obtain directly interpretable inverted model. What I mean by that is that because the inverted density values are now directly interpretable, so we can easily assign mythological or geological labels to each features. That will make the interpretation much more reliable and less subjective. Here's another relevant problem in the context of integrated imaging of multiple types of geophysical data. So on the upper left here, this is a simple density model. So I just use the SEG salt model and modify it a little bit. So in this case, we have 0 background, a sedimentary background, have a 0 density contrast. And for this salt body, the density contrast is about 0.6 G per cc. And this is the corresponding velocity model. If you compare these two models, the density, the salt body, they are structurally identical. And they are uniform, the densities and velocities are uniformly distributed within the salt body. So this is our true model. And if we plot up the density values against velocity values, this is what you will see here. You will see two dots at these two locations. This dot corresponding to the sedimentary background, and this dot corresponding to the salt body. So now a similar research question we can ask is, what if we know the following information? First, what if we know there are two possible types of geological units? And what if we know that average physical property value for each geological unit are such and such? So the question is, how can we incorporate this type of information into, in this case, joint inversion? This is a challenging problem if you really think about it, because first of all, we have multiple types of physical relationships in this area. In this case, we have two. Well, that will be a problem because if there are two possible relationships between density and velocities, how are you going to know at which area of the model region you're going to apply which one of these? So that's what I wrote down here. It's very difficult to specify the spatial applicability of the multiple relationships a priori. Also, and because of this, the information we have is actually statistical in nature because there's no location information associated with the information here. All we have are these values. We know that the density and velocity value can only be this and that, but there's no spatial information associated with it. So that's what I meant here by statistical. So just a quick summary here. The Tikhonov inversion provides a very convenient way of recovering a geophysical model based on geophysical data. It has been used a lot and very successfully in many problems, but it has limited functionality in terms of allowing us to incorporate statistical a priori information. One of the examples of the statistical a priori information is this one I showed you here. So we think that we need to develop a new set of inversion algorithms that allow us to better make use of the a priori statistical information. So that's our motivation. And it turns out that machine learning can be very useful for that purpose. So next, I'm going to quickly talk about unsupervised machine learning and specifically clustering. So on this figure, what we show here is the distribution of the conductivity and susceptibility values. So we can assume that each dot here represents one rock sample, and on each rock sample we make conductivity and susceptibility values, and then we cross-plot them. So this cross-plot summarizes the physical properties, a priori physical property information we have. If you just look at the distribution of the white dots, this petrophysical data, you immediately realize that there are three clusters, right? Because we humans are really good at recognizing patterns, but that is only true when the patterns are not that complicated, and only when our data are sitting in lower dimensional space. If the patterns are complicated and if the data are sitting in a high dimensional space, we need to let the computer do the job. And that is where clustering comes into play. So with clustering refers to the a process of automatically organized data into groups. So in this case, different colors represent different clusters identified by any clustering algorithm. In addition to that, it can also automatically estimate the cluster centers. Here highlighted by all these by this red dot here. So in this case, I'm using the conductivity and susceptibility values as examples, but you don't have to be limited to that. In general, that will be your feature 1 and feature 2, whatever feature 1, feature 2 correspond to. And also here I'm using a 2-dimensional cross plot as example for illustration purposes, but you can have as many features as needed. So in this case, for example, if you have 1,000 features, then we're talking about clustering in a 1,000 dimensional space. So mathematically, clustering, there are many clustering algorithms out there that can achieve this, automatically organize data into groups. One particular clustering algorithm that I have been using a lot in the context of geophysical inversion is called fuzzy Siemens clustering. Mathematically, it can be summarized by minimizing this objective function here and subject to this constraint. I know this probably looks a little bit complicated if this is the first time you see this, have seen this equation here, but here PJ, that represents the jth data object in your data set that you want to cluster, and VK, that is the estimated center for the kth cluster, and N here, that is the total number of data objects to be clustered, and C, that is the expected number of clusters, and UJK here, that is a membership value that measures the degree of the jth data belonging to the kth cluster. So without going into details, it suffices to say that by minimizing this objective function, we will be able to achieve something like this. So this is our clustering results. In this case, if you apply the fuzzy Siemens clustering, you will be able to get this nicely clustered results. It turns out that clustering has been used in many other areas. For example, one of the applications of clustering is the Google News. So if you go to Google News or news.google.com, this is you will see something similar to this. On the left-hand side here, you see many tabs. For example, here you have US, world, local, technology, sports, science. You have different categories, right? If you click any one of these tabs, for example, in this case, I click science, this tab here, and this is what you see here. So within this under this category science, these are the news articles that Google collected yesterday. So one of the stories in this category is something about the Greenland ice melting. And if you click this view for coverage, you will be directed to a web page where you see all the different news articles or different news reports on the same topic from different agencies. For example, you have an article from face.org, from CNN, from Washington Post, etc. So what happens behind the scenes is that there is a clustering algorithm applied to the thousands or hundreds of thousands news articles, and it automatically groups the news stories into different categories. So when readers like you and me, when we go to news.google.com, you will have this nicely grouped news stories in different categories. Another application of clustering is in the social network analysis. So the problem here is that given your Facebook friends, is it possible to identify the most cohesive groups? The answer is yes. We can use clustering to easily achieve that. So the cohesive group, the people in the cohesive group, they tend to know each other. So they are more familiar with each other in the same group. Another more lucrative application of clustering is the market segmentation. So nowadays, many companies like eBay, Netflix, or Amazon, they have a huge amount of customer database. So one thing that they do is to use clustering to automatically classify or organize or group customers into different segments. All the customers in the same segment, they tend to have the same buying habits. So based on that, they can develop the more targeted advertising strategy or marketing strategy so that they can sell their products more efficiently. So back to our problem here. So this is one of the first motivation example I showed you earlier. In this case, we have two rock types. Their possible density values are 0 and 0.4 G per cc. Using the terminology of clusters, we can summarize this information in this histogram by the following. There are two clusters. So each cluster would correspond to one geological unit. And we also assume that we know the cluster centers, which are, in this case, 0 and 0.4 G per cc. So here are the cluster centers. You can understand the cluster centers as average density value for each geological unit. So this is how we interpret the a priori pyrophysical information summarized in this histogram using the language of clustering. So now I think we're ready to formulate the cluster inversion. So again, the goal is, remember, the goal is to estimate a model. First of all, that can reproduce our measured data. So therefore, we still have this data emissive term, which is simply a measure of the difference between the measured data and the predict data. But in the meantime, we also want the inverted, for example, in this case, the density values. We want the inverted density values to show two clusters. Therefore, we have this term here also in the objective function. And this term is simply what you saw earlier when I talked about the clustering objective function for clustering. So this is just, I just copy and pasted that objective function here. So that's that. We also want the clusters to be located at target positions. Therefore, we have this term here. So this term is simply a measure of the difference of the recovered cluster locations and the desired or target cluster locations. So by minimizing the difference between them, we are constraining inversion in such a way that the inverted values are going to show clusters at the target positions. The target positions in this case are symbolically represented by the TK. So TK represents our target positions. We also need the regularization term to stabilize the inverse problem. So therefore, we end up with 4 terms in this objective function when it comes to cluster inversion. So here, a quick summary here. So here, C, the superscript C here, that is the number of clusters that we expect to see among our inverted values. And TK, that is our target cluster centers, or the a priori average physical parameter values for each geological unit. So back to this problem here. In this case, we know that, as I told you earlier, we can summarize the information in this histogram by assuming C equal to 2, that is 2 clusters. So C equal to 2. We also know that the possible density values are 0.4. Therefore, our target cluster centers are 0 and 0.4. So with these 3 parameters, you can now go ahead and minimize this objective function. And if you do that, this is what you will get. So in the middle panel here, these 2 figures shows the results from the cluster inversion. So in this case, you see that we recover a much more compact anomalous bodies if you compare this model with the smoothness based regularization inversion results. Also, if you look at the distribution of the inverted density values from cluster inversion, we do see two peaks at the target location 0 and 0.4. The distribution in this plot is much more consistent with the true distribution here. So now, so that's the cluster inversion applied to a single data type. So for the next step we took is to extend that clustering inversion to joint inversion, where we have multiple types of data. Again, this is the SEG sort model I showed you earlier. In this case, we have 2 clusters because you see two dots, one corresponding to sediments, the other one corresponding to salt body. So therefore, C equal to 2 means that we have 2 clusters or 2 geological units. Also, the T1, T2, that is the target or the average physical average density and velocity values for each geological unit. So with that, we can go ahead and formulate the joint inverse problem. Again, in this case, we actually want to estimate 2 models, and we want each one of them is able to reproduce their respective geophysical data. Therefore, we will have 2 data emissive terms, one for each type of data. In addition to that, we also want the inverted, for example, the density and velocity value to show 2 circular clusters. Therefore, we will have this term here again. You saw this term earlier in the formulation of the single data type cluster inversion, and you see it here again. Also, we want the inverted or the estimate. We want the inverted cluster to be located at the target positions. Therefore, we have this term here. So this is a term that measures the distance between the target positions, cluster positions, and the inverted cluster positions. Also, we also need the 2 classical regulation parameters, regulation terms to stabilize our inverse problems. So this is the objective function we end up with if we want to perform the joint cluster inversion. Again, so here again in this case here, C is the number of the expected clusters, or the number of the expected geological units. TK, that is the target or the a priori average physical parameter values for each unit. This information, TK, can be determined from a priori petrophysical measurements. So with application to the soft model, in this case, C equal to 2, T1, T2 can take on these values. So now if you go ahead and minimize this objective function, you will end up with something like this. So on the left, the two models, on the left-hand side, these are from the separate inversions. So this model shows the inverted density model from separate gravity inversion and the velocity model from separate seismic travel time inversion. So in this case, if you look at the density model, we recover this big blob, a smoothness. You see a lot of smoothness because of the smoothness regulation term. There's no detailed structure of the soft body recovered. Also, if you look at the velocity model from separate travel time inversion, we recover this dipping flank, but we're missing this top part. On the other hand, if you look at the jointly inverted density and velocity value, and compare that with the true density and velocity models, we in this case we are pretty happy with what we obtained from the cluster inversion, especially if you look at the jointly inverted density model. We recover all these detailed structures from joint inverse problem using gravity data. So with gravity data, you don't normally expect this kind of detail to be recovered, but we did in this case because of the clustering inversion we used. So here's a movie that shows the jointly inverted density model after each iteration. So what you will see here is that in the first few iterations, we don't see much detailed structures of soft body recovered. If you compare that with the separate inverted model, this is pretty much similar to the density model from separate inversion. But as the iteration goes on, you see that more and more detailed structures are being added to this model. And now what inversion is doing now is trying to make the recovered density values in both the background and soft body to be more consistent with the true values. And at the end of inversion, we recover this soft body with all these details, and also the dipping flank is almost perfectly recovered. And here's another movie that shows the distribution of the jointly inverted density and the velocity values. So here, what you see here, each yellow dot represents the recovered density and velocity value at one model cell, and these two red dots represent the true values. Okay, so this is what you see here. That is the distribution after just one iteration. So we don't see any clustering features. They just scattered. They just scattered over this this plot. But as the iteration goes on, what you will see that the yellow dots are moving toward one of these two yellow dots, as if they were attracted to these red dots. That's our target locations. So now you're seeing that the clusters are being formed. That's because the cluster constraints we put into the inversion are taking effect. So at the end of inversion, you see these two well-defined clusters among yellow dots. So a quick summary here. So the cluster inversion or the joint cluster inversion, it is a highly constrained inverse problem. So we constrain inversion very strongly. In the sense that the clustering terms here, these two clustering terms here, will force or encourage the inverted values to form clusters at desired locations, which is represented by TK. And at the end of inversion, the distribution of the inverted values will match the truth. So that's the joint cluster inversion. what we do is that we combine the clustering with two types of data. So the next inversion algorithm I want to briefly talk about is the magnetization class inversion. So in this case, we are using class inversion to solve the magnetic remnants problem. So this is a general formulation for the magnetization inversion. So in this case, we are interested in recovering a distribution of the three-component magnetization vectors in the supersurface based on the observed data. In this case, it could be any type of magnetic data. For example, magnetic total field anomaly. This is the deterministic term that you have seen many times. And this is, again, the classical smoothness-based regularization term. So this is a general formulation of the magnetization inversion, or I will refer to this as unconstrained magnetization inversion. So to illustrate how this works, I simulate this total field anomaly resulting from one anomalous block with remnants. And this figure in the middle, that shows the recovered magnetization vectors from the standard or unconstrained magnetization inversions. Each of the cones that you see here represents the magnetization vectors recovered from the inversion. And the head of the cones represents the recovered directions. And this color represents the effective susceptibilities. This, I don't know if you can see this, but this gray box here represents the location of the true position of the target body. So if you just look at the effective susceptibilities, we actually recover the anomalous body pretty well. We recover its locations and its spatial extents. But if you look at the recovered directions, which is summarized by this polar plot, and in this case, the azimuths corresponding to the declination and the radius corresponding to the inclination. So each of the yellow dots represent one of the magnetization directions recovered. So you see that the recovered distributions have a strong degree of scattering in this polar plot. They just scattered everywhere. And for comparison, this yellow triangle here, that represents the true magnetizing directions. So in this case, the lessons we have learned is that the recovered magnitudes are highly interpretable, but the directions are highly variable, as you can see here, and therefore it's not quite interpretable. So we want to improve the recovered magnetizing directions. To do that, we make a basic assumption, that is, in the area of interest, there are only a few possible directions, magnetizing directions. For example, in this case, there are only two directions instead of many directions in this polar plot. In addition to that, we also assume spatial coherence among the recovered magnetizing directions. In other words, if the two model cells, they are adjacent to each other in spatial domain, then we expect their magnetizing directions to be similar. So these are our basic assumptions, and we can now go ahead and formulate the inverse problem by incorporating these basic assumptions. So here's the standard magnetization inversion I showed you earlier, the objective function. So to improve the estimation of directions, we added two more terms here. These two terms should be familiar to you now because you have seen these two terms, similar terms, at least twice from previous slide. So here we have this third term. Again, this is just from the clustering, fuzzy Siemens clustering, and this is this fourth term. That's just a measure of the difference between the recovered direction and the target directions. So the purpose of these two terms, or these two clustering terms, is to limit the recovered directions or magnetizing direction to only a few possibilities. So remember, this is the assumptions we made, and this is something we set out to achieve. And we also want to encourage region-wise consistency in spatial domain. So here's an application example here. In this case, we applied we have this airborne magnetic data, and we apply the magnetization cluster inversion to this set of data, and this is the anomalous bodies we recovered in 3D domain. So here, the different color representing the representing the effective susceptibilities. In this case, I assume 3 clusters, and here is just a depth slice at I think at a depth of 210 meters. This black outline that indicates the location of the unknown all bodies. So what we see here is that the recovered anomalous bodies from the cluster inversion are highly consistent with the locations of the known all bodies. And here, this 3D volume that shows the recovered magnetization direction vectors at the same depth. So again, the color representing the effective susceptibility, and the head of the cone represents the recovered directions. So what we see here is that we do observe these spatially coherent magnetizing directions. So this is, if you plot up the recovered directions in this cross plot of inclination versus declination, this is what you will see. Again, we see 3 well-defined clusters because I assume 3 clusters. So there are 2 questions: how to determine number clusters, and what is the uncertainty of the recovered directions. So to do that, I took a very empirical approach. So what I did is that instead of just assume 3 clusters, I also tried 2, 4, 5, 6, 7, 8, 9, also up to 100 clusters. So here I'm just showing you the results from 4 different assumptions of the number cluster. This is the recovery direction when assume 2 clusters, 3 clusters, 4 clusters, and 5 clusters. So now let's take a look at the recovery direction in spatial domain. When we assume different number clusters. So this is recovered magnetizing direction at this depth, 160 for 2 clusters. We do see 2 dominant directions. This is one, and this is one. This one almost pointing horizontally, and this one pointing like 45-degree downward. And this is what happens when you assume 3 clusters, 4 clusters, and 5 clusters. So if I go back and do it one more time, this is recovered direction for 2 clusters, 3 clusters, 4, 5. There are a few. I want to make 2 observations. First, recovered magnetizing direction do show region-wise consistency, no matter how many clusters we assume, which is a good thing. And also, we observe that assuming different number of clusters does affect the recovered magnetizing directions. However, I do hope that you can also see that at some regions, the recovered magnetizing directions are much more robust or much less affected by the assumed number of clusters. For example, if I do one more time, if you just focus on this area here, the recovered direction is pointing downward. This is for 3 clusters, 4 clusters, and 5 clusters. So what we see here is that there seems to be a spatial variability of the sensitivity of the recovered direction to the assumed number of clusters. In some areas, the recovered direction are more robust against the assumed number of clusters. So because I recovered 4 3D volumes, so at each model cell I have recovered several different magnetizing directions. So we can consider the unknown magnetizing directions as a random variable. Because I did 4 inversions, so I have 4 estimates of the magnetizing directions at each model cell. So with that, we can calculate the simple statistics, for example, the mean and standard deviation. And we do that for all the model cells in the 3D volume. And we will end up with something like this. So this is a standard deviation of the recovered magnetizing directions in 3D volume. Here is this deep blue corresponding to the low standard deviation values. In other words, the recovered direction in this area is much less affected by the number of clusters. So if we compare this low standard deviation zone with the geological map, here's a major feature in this geological map is this thrust fault that stretches northwest and southeast. You notice that all hydrothermal alteration zones are distributed along this fault. These are where most of the mineralization deposits are located. So if you compare the shape and location of this low standard deviation zone and this all these hydrothermal alteration zones, they're highly consistent. So quick summary here. So what I've presented here is that we have developed a new set of inversion algorithms by combining classical Tikhonov regularization inversion and machine learning. In this case, the unsupervised machine learning. And I showed you 3 different inversion algorithms: cluster inversion of a single data type, cluster inversion, a joint cluster inversion when it comes to multiple types data, and also cluster inversion applied to magnetic data for solving the remnants problem. So this represents an interdisciplinary approach to solve some of the challenging problems in geophysics by using the algorithms that have been well developed in machine learning community. So here's just a few of my thoughts on the road ahead. So I really think that interdisciplinary is the key to solving some of the grand challenges we are facing today in earth science. Speaking of road ahead, in the context of geophysical inversion and machine learning, I just want to I just want to mention a few things here. So in my talk, I talk about how clustering can be used to in the context of joint inversion, in the context of geophysical inversion, to solve some of the problems. But there are many other algorithms, methods out there in machine learning that can potentially also be useful for solving our geophysics problem. For example, one example here is Gaussian mixture models. So you can consider Gaussian mixture models as a probabilistic clustering algorithm. This is widely used in image segmentation and speaker recognition problems. And it has also been used in geophysics very recently. For example, in this paper by Geophysical et al. In 2017, the authors used Gaussian mixture models to summarize the multimodal petrophysical data. In this case, what you see here is that this is a cross plot of density contrast and magnetic susceptibilities. You see many 5 or 6 different clusters, each cluster representing one geologic unit. And they were able to use Gaussian mixture models to capture this complicated petrophysical data and incorporate that into joint inversion. Similarly here, last year, Aztec and Oldenburg, they used a similar idea to model the multimodal petrophysical data. So these 2 contour lines and these 2 sets of contour lines you see here represent 2 Gaussian models. And another thing that might be very useful for geophysical inversion are the neural networks. So you probably have heard this term quite a lot nowadays because neural networks have helped enable many of the breakthroughs we see nowadays. So I just want to quickly mention one piece of work here by Hansen and Caldwell. This paper was published in 2017. In this paper, what the author did is that they are interested in Monte Carlo probabilistic inverse problem, namely Monte Carlo sampling of inverse problem. But the problem is that for 2D problems, the Monte Carlo method are not really applicable because of the computational cost involved in forward modeling. Because if you want to apply a Monte Carlo MCMC sampling, you need to do a lot of forward modeling. If some of them are very computationally expensive. So in this case, they consider the cross-hole ground penetrating radar, or GPR. The forward modeling of the first travel times are computationally expensive, which makes the Monte Carlo methods infeasible for this 2D model. So, but what they do is that they use a simple two-layer neural network to approximate the computationally expensive forward modeling, and use that as the approximation or as a proxy to the forward modeling. The good thing about that is that the neural network-based approximation is very fast. And because of that, they were able to apply Monte Carlo method to the inversion of the GPR travel time. So this figure here shows the samples drawn from the a posterior probability density functions. So just some quick concluding remarks. I think that we are living a very exciting time. We have access to unprecedented amount of data or big data. We also have access to unprecedented computational resources. And you have seen many exciting breakthroughs in many areas. For example, computer vision, speech recognition, natural language processing, robotics, including self-driving cars, etc. I believe there are plenty of opportunities out there that we can make use to make breakthroughs in geophysics, especially in geophysical inversions. You just need to be creative and have an interdisciplinary mind. So with that, I would like to acknowledge, thank Alini Mello as well as SCG Latin America Committee for inviting me to give this presentation. Also, I would like to thank Laurie for setting up the webinar. With that, I would like to answer questions you may have. Thank you for your attention.
Thank you very much. If you have a question, you can either raise your hand in the webinar interface or enter it in the question and answer box at the on the toolbar, or just put it in the chat.
So one attendee asked if the slides will be available. So I don't know what's the policy. What is SCG policy on this? Is this are we supposed to make the slides available, or is that?
I think the slides are yours, but the webinar will be available in its entirety.
So the webinar was recorded, right?
Yes.
Okay. Yeah. So you will have access to all the slides, everything I showed here by look at the recorded video.
Yes. All right. So we have a question from Muhammad. We'll unmute him, and he can ask his questions. Go ahead, Muhammad.
Hi, I have a question about using clustering, like Euclidean distance clustering. It's better or not than focused fuzzy clustering? Thank you.
I'm not quite sure if I understand correctly. So you are asking about clustering. What is your question about clustering?
Could you rephrase, Muhammad?
Okay, I asking about using Euclidean distance clustering in inversion of magnetic and gravity data, 2D magnetic or 2D gravity data inversion. Like if I have more or three cluster, the first one is positive density, the second one below the first is negative density, the third one below the second and positive density. Will be give answers or not?
Okay, so I'm trying to understand questions. You're asking about clustering. So in, the basic idea is that we assume that if I can go back to my slide, so the basic idea is that we assume that we have access to the petrophysical measurement. If you visualize or plot up your petrophysical data, if you see clustering features, then this method is available, no matter how many clusters you see. So this method is generally applicable to any number of clusters. Of course, this method will be best applicable if the clusters are well separated. So yes, I think this can be applied to any type of data, including even if you have negative density contrast or something like that. Okay, I have a few other questions here in the Q&A window. So one of Charles asked, if the last term is left out, how much does this affect accuracy of the inversion result? So that's a good question. So this last term, remember this last term measures the difference between the inverted cluster centers and the target cluster center TK. So TK is something we know from petrophysical measurement. That is something we know before inversion. But in practice, we don't always have access to high quality petrophysical data. Or even if we have, sometimes they don't show good clustering features. So in this case, we can turn off this term, or basically leave out this term, and we just let the inversion to decide where it wants to put these clusters. Of course, you can imagine that in this case, because we don't have any guidance from the a priori particle physics data, so you can imagine that you will still be able to see well-defined clustering features, but you can imagine that their locations will be a little bit off if you compare that with ground truth. There's another question from Chi. She asked about joint inversion, asking about, have you tried joint inversion for more than 2 types of data sets? So far, not yet, because I personally didn't have access to a data set involving 3 different types of geophysical data. So I have been only be able to apply this method to situations where we have 2 types of geophysical data, for example, magnetic IP or gravity magnetics. But I want to see that this method is generally applicable to any number of geophysical data type. It's just that in this case, if you want to invert 3 different types of geophysical data, you just need to add another pair of phi d and phi m. For example, in this case, you would have phi d3 plus phi 3, phi m3. And these 2 clustering term will remain the same. Okay, another question from Philip, asking about the data size and time spent inversion. For example, on slide 47, on slide 47, I think this is for slide 47, joint inversion took 302 iterations. And what about the time in the last real time with clustering inversion? Finally, what programming language did you use? Okay, the data size for this one, okay, for this particular one, let me see. I did this quite a few years ago, so I don't remember exactly number. But you're right when it comes to joint inversion, because this is the nonlinear inverse problem, because the clustering process itself is iterative, nonlinear. So you have to use some kind of iterative minimization algorithm. In this case, I use the Gauss-Newton method. So it turns out that it took a lot of iterations. In this case, 302 iterations. If I remember correctly, this I used MATLAB for this particular example on my single workstation. It took a few hours, 1 or 2 hours. And for this real data example on the magnetics, for this one, I'm using Fortran 95. And for this one, I think if you're talking about magnetizing cluster inversion, let's say assume 3 clusters. This particular one took half a day or to 1 day. I forgot the exact time, but on the order of that, about 10 hours. But I want to point out that the more clusters you assume, the less time it requires. So for example, if you assume 100 clusters, it will be done within, let's say, 10 minutes. Okay, another question also about the computational expense. Can you comment on the time associated with this cluster inversion when compared to Tikhonov? Yes. So for Tikhonov, especially when you talk about gravity magnetic inversion, the Tikhonov inversion is pretty quick. For even for large-scale airborne magnetic gravity inversion, you can get it done. You can get the inversion done within 1 hour or 2 hours, assuming that you have all the required data available, all the required data in the correct data format. So a few hours will be enough to do the large-scale inverse problem. But for a cluster inversion, I would say that it took a lot more time. Tens of hours for this particular example here. In this example, we have 2,000 magnetic data points, and we are inverting for about 3 million model parameters. It took me about 10 to 15 hours. The reason is the following, because for Tikhonov inversion, you only need to update model M at each iteration. But for cluster inversion, remember I put 3 symbols here, M, UJK, and VK. These 3 are all unknowns. So UJK, that is membership value, VK, that is cluster centers. So for cluster inversion, at each iteration, we need to update all 3 of them. So that's why it is slow. Yeah, it is slow.
Okay, I think you have another chat question. Actually, you have two. I think, did you address community's first question in terms of computational expense?
Yeah, I just did,
All
yes.
right. And then Mohammed asked another question as well.
Oh, Mohammed asking another, okay, let me see. Mohammed, so Mohammed is asking about if fuzzy class inversion will live plausible model from one data like gravity, for example, or must use joint inversion with one other geophysical data. Also, if code fuzzy seamless classroom of MATLAB available or not. So I guess you're asking if so you want to compare you want to see what happens if I apply fuzzy cluster inversion to one type of data as compared to joint inversion involving multiple types of data. So I guess that really depends on the problem you're trying to solve. For example, for this particular, if I go back to this motivation example here, this is a very simple example. Although this also in mineral exploration this is not a bad approximation of the mineral exploration problem that we deal with. So in this case, I think the applying the class inversion to one single data inversion will result in reasonable models. But if you work on more complicated example of problems, for example, if you want to if you're interested in subbasalt imaging, for example, this one, this is the basalt sequence, and this is the subbasalt sediments. This is where we are. This is what the target that we are interested in. In this case, the single data class inversion will not work, especially if you apply the class inversion to seismic data. It will not work simply because for all the seismic data, most of the seismic energy, when it reaches the top of basalt, most of them will be reflecting back up and picked up by the seismometers on the ocean bottom. Very little seismic energy can penetrate the basalt and eventually reach the subbasalt sediments and then reflect back up and eventually pick up by the seismometer. So in this case, the single data inversion, even with class inversion, will not work because the seismic data simply does not contain any useful information about subbasalt sediment. In this case, you must use joint inversion or integrated or some kind of integrated imaging of seismic and EM. So it depends. And about the codes, the fuzzy seamless clustering of MATLAB available or not. So at this point, it's not available, but I'm planning on making it public available by developing open source version of the code in SynPack. Yes, we are using. I'm going to use SynPack as the general computing framework to make this open source.
Okay, well, I think we're just about out of time. We will have time for one last question if anyone has one. All right, it doesn't look like we have any more questions. So with that, I think I'll wrap it up for us. Thank you, Dr. Sun, and thank you all for attending the SEG Latin America Regional Advisory Committee's webinar. As part of our webinar series, Recent Advances and the Road Ahead, please look for our social media posts to register for next month's interesting talk. Thank you again for attending today, and thank you, Dr. Sun, for an interesting presentation.
Thank you, Laurie. Thank you, everyone.
Yep. Have a great day. Bye-bye.